Next, we'll discuss how to use the limited population growth model, also known as the logistic equation. So previously, we talked about the type of differential equation that we have to solve to find the function that represents the population at time t when an additional constraint is given. So this is the equation, and here we have its solution. Here I wrote the solution in two different ways. Depending on your preference, you may like to use one or the other. And down here we have the explaining of all the letters. So L stands for the carrying capacity, L stands for limiting. However, letter K is frequently used. K stands for capacity, I guess, and initial population is P0, and R is the growth rate, assuming if there was no constraint. So let's take a look at this problem, and let's find the solution. And by the solution, they mean the function that represents the population at time t. So again, we don't need to solve the equation from scratch because we've done it already. So let's just identify what's what. So the P0, the initial population, is 28,362. K, which I previously labeled as L, is the carrying capacity, which is 7 million. And the growth rate R, it's 2.19. So we literally have everything we need to plug in. So carrying capacity multiplied by P0 and all that divided by carrying capacity minus P0 and here we're gonna write e to the power negative 2.19t, and we're gonna add P0, which is 28,362. So this is our solution. We can totally compute all these numbers. But the easiest way to avoid some heavy computations will be to reduce everything by 28,362. So we can rewrite P of t as, again, I'm just dividing everything by that number, including the numerator and the denominator. So in the denominator, what we have in parentheses, everything inside has to be divided by that number. And if we put that in the calculator, we should get 250. So simplifying everything will give us this answer. However, we can also rewrite the same answer with e to the power 2.19t here and here. So these two are equivalent answers. Now that we have the solution of this equation and the function that represents the population of squirrels, we can answer the following questions. So let's use this solution to estimate the population when t is equal to 5. So once again, let me just copy this equation. I'm going to use this form because it only has one presence of t, which makes it easier to deal with. So I'm just going to actually copy this over. And to answer the question that we are asked, we simply have to find the value of this function at 5. So we just plug in, literally, instead of t, we replace t with 5. And there is no easier way to do this than putting it all into Wolfram Alpha. So let's carefully type this up. Hopefully I'm not making a mistake here. I guess this is a scientific notation, so let's see. Yeah, I guess we are, this is close enough, right? So we have 7, I missed that. So this will be the answer in scientific notation, but we can totally write it out like this. Another type of questions that we can answer with the equation is going backwards. So given this formula, can we find how long it will take to reach the 99% of the carrying capacity? And again, why we're asking about 99% of the carrying capacity? Because it is possible that you may never be able to reach the carrying capacity due to the nature of this process. So when we are asked to answer this question, what exactly we're asked to solve? We need to solve this equation. So my population has to be equal to 99% of the carrying capacity, which is k. So let's set it up. And k was actually the same number that we already have in the denominator, in the numerator. So, which makes it nice, we can just get rid of this number. And now to isolate t, we have to take the reciprocal. So we have 249e to the power negative 2.19 plus 1 is 1 over 0.99. And I'm just going to do algebra here real quick, right? So we're going to subtract 1 from both sides. Then we're going to divide everything by 249. And then we're going to take natural log of both sides, right? And then we're going to divide everything by negative 2.19. and this will be the solution of this equation. So we just now have to carefully evaluate it, and I'm going to use Wolfram Alpha again. So we're going to have ln of something. So we're going to have a numerator and the denominator. In the denominator we're going to have negative 2.19, and in the numerator we're going to have ln of something, and that something will be also, we'll have a numerator and the denominator, and in the denominator we're going to have 249, and in the numerator we're going to have a fraction minus 1. So it seems like the answer is .61, and since we're not given the units of time, our answer will be approximately 4.6 whatever units of time implied by the model. So we discussed how to use the logistic equation, which is the solution to the differential equation, which we call the logistic model. And we discussed how to use it in, first of all, how to find it, and then how to use it in 2 different ways.